Hi folks, so thus far in the semester everything's kind of built up on itself. We've got electrostatics, which leads directly into circuits. Then we did magnetism and related it to electricity and circuitry. Right now I'm going to take a quick step away and talk about something seemingly unrelated, waves. But then we will of course loop it back together with electromagnetic waves, which is light, and that'll round out the semester. So, before we can talk about waves, we need to talk about a medium. Now, all that a medium is what the wave is traveling through. And a lot of waves require a medium and can't travel without it. Not all of them. Case in point, electromagnetic waves, that doesn't need a medium, but most of them do. Something to travel in. It basically carries the wave. It doesn't create the wave. Fun fact, the media is plural of medium. And they just carry and deliver the news. Their task is not to produce events that create the news, mostly, but just to carry the news to you, just like a medium will carry a wave to you. You'll encounter terms like pulse versus wave. A pulse is a single disturbance, one big push that travels like a wave. A wave is a series of pulses, one after the other. Some terms that you need to know. You got to know what a crest is. That's going to be the top of a transverse wave. A trough is the bottom part of a transverse wave. Now, a wavelength is from trough to trough. What's the distance there? From crest to crest. What's the distance there? Now, wavelength can get a bit more complicated than that, especially if you're dealing with, let's say you've got a known quantity at some midpoint between a crest and a trough. The definition of a wavelength is more strictly the distance a wave travels before it starts to repeat its motion, right? So if I'm at a crest and then I travel down a trough, back up to a crest, if I were to keep going, I'd travel down again. And I've already done that motion, so I've already completed a wavelength. Same deal with a trough. I could travel up to a crest, back down to a trough, and if I kept going, I'd begin moving up to a crest again. I'd repeat some motion I already did. So I've traveled a wavelength. When you're at a midpoint between a crest and a trough, you actually need to travel 2 midpoints over. I would go from the midpoint down to a trough, up to another midpoint, but if I kept going, I'd continue traveling up, and I haven't done that yet before. Until I pass by a crest, get to a midpoint again, then if I were to continue, I'd go down to a trough. So from midpoint to 2 midpoints away is also a wavelength. That's going to be pretty important when we start doing standing waves and looking at node to node, antinode to antinode type of stuff. But we're not quite there yet. Also, you need to know amplitude. Now, amplitude is not the distance from a crest to a trough. It's just from a crest to the midway point, or from the midway point to the trough. Basically, the height difference between the crest and the trough is 2 amplitudes. Now, there are a couple of different types that we're going to encounter in this class. There's transverse and there's longitudinal. Transverse waves have motion perpendicular to the direction of the wave, and here's what I mean about that. Think about a bunch of people at a sporting event. It's March Madness. And they're all in the crowd, and all of a sudden someone decides they want to get the wave started. So they begin it on one side of those stands, and the first person raises their arms up. Then as they put their arms down, the person next to them puts their arms up. And it continues like this down the entire row of people. So each person's arms are actually traveling just up and down. So those are like the particles that make up the wave, just traveling up and down. But the wave itself, the overall motion, is traveling to the right. So that's a transverse wave. And there are lots of other examples of this sort of thing happening. Now, a longitudinal wave is where particles travel parallel to the wave motion, like a little push and pull going on. So some examples of this would be like a sound wave, which we'll talk about in just a little bit. but the particles travel left and right as the wave travels, let's say, to the right or something like that. So transverse waves are kind of the more classical version of waves with the crests and the troughs and all of that. Longitudinal waves actually consist of regions of compression where the particles are tightly squished together. Let's say one region was pushing left while the other was right. A little bit in the middle will get caught squished up together. And it has rarefactions, which is where the particles are a little bit more spread out. And a particle will travel from compression to rarefaction, much like one would travel from crest to trough as a wave was passing through it. A few more wave terms that you need to know. The period is the amount of time it takes the wave to travel one wavelength. This should be really familiar. Kind of like the period with circular motion was the amount of time it took to travel once around a circle. Now, the frequency is, just like with circular motion, the exact inverse of the period. The frequency in this case will be the number of wavelengths that pass by at any given second. The wave speed is how fast that wave pulse is moving. Now notice that this is not the speed of the particles. If we're talking about someone in the middle of the wave, the particles will be traveling up and down, and they'll alternate between some velocity in the middle and zero velocity on either side, so they can change direction. That's not what I'm talking about when I talk about wave speed. That's how fast the pulse is moving. And wavelength is, again, the distance until the wave repeats its motion. And that'll be measured in meters. All right, so how do these terms actually combine together? Well, I already know that frequency is 1 over the period. That's the inverse. Also, the wave speed, the velocity, can be found using the idea of wavelength and frequency. Frequency I already know is in 1 over seconds, or hertz, and wavelength is already in meters. So to get meters per second, I just multiply the two of those together, and I end up with an equation V equals lambda F. This is an equation you're going to have to use a lot in this unit. Wave speed equals wavelength times frequency. Now, when waves themselves are combining, it uses this principle of what's called superposition. So let's say a crest meets a crest, or a trough meets a trough, you get constructive interference. A small crest and a small crest meet together, you get a mega crest. Let's say it has an amplitude of, say wave 1 has an amplitude of 1, wave 2 has an amplitude of 3. When they collide, crest to crest, you get an amplitude of 4. Fancy that. Same deal when troughs and troughs meet. But if a crest meets a trough, then you get destructive interference. The wave amplitudes will decrease, or they might end up canceling entirely. The last little bit I want to talk about on this one little video is a wave on a string. That's a special example. You get a velocity that's equal to the square root of the tension in the string times the length of the string all over the mass, and that's the square root of the whole thing. So square root of F times L over M, where F is the tension in the string, L is the length, and M is the mass of the string. But this can be a bit misleading. If you want to change the wave speed of a string, be like, hey, let's just add more length. Problem with that is if you add more length, you also add more mass. So a lot of wave speeds are independent of pure length and mass, so here's a better way of writing the equation. We can find a ratio of the mass to length. That's what's called the linear mass density. It's characterized by, since you haven't seen this Greek letter enough, mu, and mu equals m over L. So I can rewrite my wave on a string equation as the velocity equals the square root of the tension in newtons of the string divided by the linear mass density, which is just mass per unit length. So that'll be in units of kilograms per meter. How many kilograms am I going to get for every string of meter I get for this string? So we'll talk more about waves in just a little bit. See ya.